answer for the second part. This is B term, right? B part. Then C part, find the power factor. Power factor calculation is nothing but cos of this angle, correct? The 0.6 degree is going to be 0.833. Power factor is 0.833. Being an inductive load, because when we talk about in this one power factor, they call as one is called leading power factor. This is applicable to capacitor. If you supply, I take a AC voltage, supply power to a capacitor. AC voltage is a capacitor. This is V input. This is the I flowing to capacitor. So the I equal to V divided by V in divided by XC, where XC equal to 1 divided by 2 pi FC. Okay. This current will be phase shift of 90 degree. That is called as leading power factor. Correct? It will be a plus 90. The phase angle between the voltage and the AC voltage supplied to the capacitor, current flowing to the capacitor. I can call it VC applied voltage. V in and IC current flowing. This I call VC voltage capacitor. The IC and this one will be 90 degree phase shifted, being a capacitor. In that case, that is called as leading power factor. Correct? If you compute this one, that is. So in case of inductor, instead of this one, I am having an inductor coil. The current is the power factor is a lagging power factor. Okay, so this minus sign represent lagging power, but if the plus sign, it called leading power factor. The value is cos of this angle. Cos of this angle is a power factor. The sign minus means it is called as lagging power factor. This is called as lagging power factor because there's a minus sign. If the angle is plus, again, if you find out, when you find out the power factor, take the value only directly, cos of this value, depending on sign, you say whether leading or lagging. Correct? Here it is lagging power being an inductive load. So this is for information only for capacitor. Okay, already with that. Then D part, what D part is input power, P input power. Total power supplied, already we saw the equation. Root 3 times VT IL into cos theta. So we know, then we can substitute root 3. VT is terminal voltage already given here. What the given is called this is VT. Okay, the VT we can substitute directly here. So the terminal voltage is going to be 460 multiplied by 460 multiplied by the current, correct? IL already we computed. That is nothing but this current what we computed. This is current flowing, correct? This is the current input current supplied by this one to the stator. So we are computing input power. Pin is nothing but input power supplied to the motor through the stator coil. Okay, so this is going to be 18.88. Okay, multiplied by cos theta. Cos theta is going to be already we know cos theta. I can substitute value itself. Power factor 0.833. Okay, so if you compute this, finally what you will get? P in is going to be 12,530 watts. P in input power supplied to motor is 530 watts. We know it. Then next what we are going to compute is we need to find out P out. P out is that we saw many power losses happening. The figure, if you see it, yeah, this is what we are doing. We compute the input power. After that, we want to find out P out. P out means you have to subtract P SCL, P core, P RCL, pre-friction, stray, any other losses. If you subtract all these things one after another, final P out will. That means you need to compute the other power losses. We input power we computed. Now we need to find out the losses so that we can find out what is the power output mechanical converter PO to mechanical power. So first thing is we find out PSCL, stator copper loss. Stator copper loss equal PSCL equal to 3 into I1 square. Extremely sorry. It is going to be P1 into I1 square into R1. That is stator resistance. We are talking about copper loss. That means dissipate as a heat. So already we know 3 is a constant. I we know that it is 18.88 whole square. And R already given. R1 is given. So it is 0.641. So many watts. So if you compute, it is going to be 685 watts. So stator copper loss. Next thing is we need to find out what is the power transferred from the stator to the rotor through air gap. We know that I have a rotor. Above that, there's a stator. In the stator only I have the coils, stator windings. Right? So it creates magnetic flux, pi stator, that goes and cuts the magnetic field of the rotor. So this is the air gap. Air gap. So this is the air gap through which, because air gap is circular, annular is this one, through which the magnetic flux from stator coil phi s is going to rotor and induces voltage. Then it creates a voltage. Then rotor creates a magnetic phi r that reacts with this and a torque is produced. Already we know that. So that how much power is transferred through the air gap, that is called PAG. PAG, power transfer to the air gap, we need to compute. PAG equal to P in minus PSCL, copper loss. So we know that this is the P in is 530 is going to be 15,530 watts minus copper loss is 685. So from this, you can find out it is 11,845 watts is the power transferred through air gap to the rotor. Okay. So that already you can see the power transfer is less than input power. Input power is 12,530. The power transferred to the rotor as a magnetic flux is only this much. Okay. Then this magnetic flux is not fully converted into mechanical torque. Some amount of torque. So P converted. The magnetic energy converted as a PAG through air gap is converted to mechanical this one. That is called P conversion. P conversion already know the formula equal to 1 minus S where slip into PAG. So if you substitute 1 minus, we know that the slip equal to 0.022, that is 2.2% multiplied by 11,845. So if we compute, this will come out as 11,585 watts. Please note that the input power this much, every stage it is reducing. You can see that some amount of power is getting wasted. So P converter also become lesser than. Okay. Then we need to find out final output. That's what they asked. Correct? P out. P out equal to P converted minus P rotational losses. Rotational loss, if you see here, what we are talking is there are many things. Correct? P this one, P core losses, stray losses through wind, all those things. These are combined together. The rotor losses, frictional bearing losses, and stray losses, windage, wind movement, and any other losses, all the mechanical losses. While talking about the problem itself, here they said that core losses are all the lumped, all the losses are lumped together 1,110 watts. All the losses in this problem they're given. If they're not given, so for sometimes, for example, P windage alone is given, windage losses, or P rotor rotor losses or copper losses are given. Something only windage losses, that means you need to compute the PRCL also, correct? PRCL formulas are given already. You can know that PRCL is given here, correct? PRCL. So we know the peak conversion, PAG minus PRC, we got it. From here we are directly going, because all other these losses are already given as a lumped parameter, correct? Since they are given, so you can find. If it is not given, so you, in that case, you need to count it the power as a rotor core loss. For that, that means you need to know I2 rotor current. You should know rotor current formula already we know. If IR is given, correct, then from that you can call I2. That is called rotor loss, and the rotor current. IR is rotor current, and I2 is called as rotor current with reference to in equivalent circuit stator coil. And that means from IR you can cut, I say A effective, correct? If I2 can be computed from IR multiplying by A effective, it is called as A effective, called as the effective turns ratio. I told you the induction motor works like a transformer. See, A effective is called as turns ratio, effective turns ratio of IM, inductive motor, correct? Induction motor. So the effective turn of inductive motor, nothing like a transformer ratio. If the manufacturer, and in the problem, A effective, I may give, in the problem is A effective is given, then you need to find out IR, correct? IR, you can find out already. If you remember, yesterday or previous day, we talked about, yeah, I given the equation, you can see here. Rotor current, you can, that means induced voltage. If rotor ER is called induced rotor voltage, that is given. Rotor resistance is given. Rotor reactance is given. Then from this one, you can always compute IR. Once IR is known, you can compute I2, effective rotor current, with reference to this one, using this IR, I2 equal to IR divided by A effective. A effective, well, I would have given like transform ratio. In the problem, I may give you. If I am given that, then you need to compute IR. To compute IR, what you need? ER value should be given. ER I given. Correct? In this problem, it is not given, because you are not going to compute some of the parameter. It is given as a lumped parameter. Correct? All the losses, like rotor, copper loss, windage loss, all those things is given as 1100 watts. If it is not given, then you need to compute each and every parameter. So in that case, I would have given ER, I would have given RR, already is there, XR is there, correct? Then you can find out IR, and in the problem, the A effective turns ratio, effective turn ratio is given some value. Then you using this I2 equal to IR divided by A effective, you can find I2. Once I2 is known, then you can find out PAG. You can use this formula also, 3 into I square R into R2 divided by this also you can find out. Correct? For wherever you want I2, then you can use the formula. Correct? You can find PRCL, you need I2. That means first you need to find I2. I2 to find out, first you have to find IR. To find out IR, what you need? The induced rotor voltage ER will be given, R2 will be given, X2 will be given, then A effective turns ratio of the motor will be given. Once it is given, you can find out IR. From IR, you can find out I2. Once you have found I2, then you can compute PRCL. Then you can use, wherever you have to use PRCL, you can use it, correct? So you can go for. So in this case, there is no need to compute all those things, and they have given together as a rotational, correct? That is the rotational means what you are talking is rotating part, which is not the rotor. What are losses? The copper loss of the rotor, the frictional loss and bearings, all those things, and windage losses together they call rotational losses. Already they're given, so we can substitute here. We know that P conversion is 11,585 watts minus the losses, lumped losses in the problem is they given 1100 watts. Okay, so then that means P output power, which is called as shaft power. This is what available to drive shaft power or output power is nothing but 10,485 watts. Okay. Suppose if you are asked to find this is in watts. Suppose if I want HP means power output in HP. If I want, you can always 10,485 divided by 746. Correct? We know from one, this is horsepower unit. So if you divide automatically, you will get 14.1 HP horsepower. For watts to horsepower, if you want, depending on what it is expected. Okay, so this is how you compute. Now that we have seen how to this one, and the next part is still there. Correct? The problem has is induced torque.
Sir, can you go to sir? The earlier slide.
Make it note, sir. Just check.
Just check.
Okay, sir. Thank you, sir.
Okay, sir.
Okay, so next part E asked is compute induced torque. Is called tau induced. Okay, tau induced, the formula is there are two formulas are there. One formula is PAG divided by omega synchronous speed. Okay, now I think in the problem they are given. What is the given? Yeah, you can find out from this. We know that omega in radians. Omega is the rotational speed at radians. F is in hertz. Omega in radians, you can easily find out. That is referred to omega S is nothing but RPM 2 pi. Okay, 2 pi into RPM 180 divided by 60. So this will yield 188.5 radians per second. Omega S. Okay, we can use this formula. So already we found omega S. We know that RPM we found, correct? This is the synchronous RPM, correct? NS we found. This is nothing but NS. From NS, omega S can be found, correct? NS multiplied by 2 pi divided by 60 will give omega S in radians per second. Okay, so one that is known. Then we can substitute that. We already have PAG. PAG already we know. PAG equal to 845 watts. And omega S is 188.5 radians. So tau induced, the load induced is nothing but 11845 divided by 188.5. This gives 62.8 Newton meters torque. So then they asked about tau load torque. That is tau load is nothing but shaft power final output P out divided by omega m. Omega m is nothing but motor's shaft speed, correct? Motor shaft speed can be computed from NR, correct? NR value, you know that NR equal to 1 minus S into NS, correct? From this, again, the omega R equal to 2 pi NR divided by 60. NR already we have computed, correct? NR, I think we computed, what is the NR value? is 1760, correct? The NR value equal to, so that means 2 pi into 1760 divided by 60. And if you compute this, you will get how much it is. Let me use calculator. It is going to be 1 mile. So it is going to be 184. 184.4 radians per second. That is omega rotor rotational velocity in terms of radians per second. Okay, this we can substitute here. And the P out already we know, correct? P out is already given. P out is 10,485 watts divided by omega m or omega, both are same. Omega m, omega rotor is same. So it is going to be 184.4. So it is going to give 56.9 Newton meters. So we got the answer. Okay. Lastly, they are asked efficiency of this motor. Correct? Efficiency is nothing but output power divided by input power. Can I go to the next slide?
Yes, sir. Yes, sir. We can go, sir. Noted down, sir. Sir,
Okay. Yeah, yes, please.
we can go ahead, sir.
Others?
Yes, sir.
Okay. So last part I asked is efficiency, efficiency of motor. Okay. Because why we are discussing more about this induction motor, correct? It is widely used in electric vehicle. One is permanent magnet synchronous motor, PMSM. Other one is induction motor. Otherwise, brushless DC motor, BLDC. BLDC, induction motor, permanent synchronous motor. So that's why we are concentrating on this. Then we will see about, equivalent is the BLDC motor. Next class we'll see. Afterwards, we'll see permanent synchronous motor. Then we will go to the semiconductor physics, that is power electronic circuit, MOSFETs, the electronic device used for driving the motors, that we'll see. Okay. So now the efficiency is eta. Efficiency generally term used is eta, you know that. Eta equal to P out divided by P in multiplied by 100. Generally by mentioned it as a percentage. So that means 10,485. Sorry, 10,485 divided by 12,530 input power multiplied by 100. You can see that 83.7%. So I can say that the efficiency is 83.7%. Have you seen any IC engine, jet engine, whether it is diesel powered, petrol powered, gas powered, or hydrogen powered? Any thermal machine will never give beyond 33%. There, the input energy is thermal, so many joules. You burn 1 liter of diesel, so many kilocalories of this is given to the engine. Only maximum thermodynamic law says that not beyond 33% or maximum 40 theoretically. Till now we are able to achieve only 33%. Even if we say 35%, remaining 65% wasted as a heat, correct? In the exhaust gas or in the body of the engine, it's radiated through body of the engine itself, silencer and exhaust gas. 65% wasted, and now people are coming with different ideas, okay, to recover this one, all these things people trying. Whatever you do, still you cannot get. But in case of electric motor, input power given is 12,530 watts, output shaft power is 10,485 watts, 83% in induction motor, correct? That is why the future is electric vehicle slowly, but the problem here is from where you will store this electrical power, from where you are generating the electric power, if you burn electric coal, diesel, petrol in thermal power station and generate electricity and charge the battery and run your induction motor, 85% is no use. Correct? Already thermal, when converted turbine, thermal power station, coal is burned, steam is created, drives this one, thermal efficiency drawn. Correct? 50% energy is gone. Then you are charging the battery. Battery efficiency also only 40%, 30%, something like that. Finally, you end up nothing. Correct? That is why now electric power cannot be said, electric vehicle cannot be said better than IC engine based in terms of efficiency and the greenhouse gas, this one, and all these things. So directly burning diesel, petrol, gas, or hydrogen in IC engine is much better than charging a battery with the thermal power station and driving electric motor. But if you produce the electrical power from solar, wind, all those things without burning, correct? So you generate green power. Green power is not burning any hydrocarbons or hydrogen. Hydrogen also at least pollution free, but efficiency is very bad. Correct? Engine, if you take heat engine, only 40% theoretically. Correct? So in that case, so that's why you are doing. But as such, still IC engines are better compared to electric vehicle till we find the better battery. Another thing, battery, we are going to see about batteries also. Efficiency of the battery, energy density, all those things going to matter. Okay. So that is okay. Now that we saw how the power given to the electric motor, input power to induction motor is converted to mechanical power as a P output after subtracting each stage, what are the core losses, wind losses, magnetics, all those things. So still we get 85% efficiency, that is better. Okay, before going to this one, I wanted to talk how the torque in the induction motor is created. Okay, already we know that the induced torque in IM, already we talked about equivalent circuit. Tau induced, already we saw the formula also. P convert, correct? That means you gave electrical power in which some amount of the power is wasted as stator core loss, as a copper heat in the copper wire of the stator. Some amount of power was wasted in the inductance of this one, and some amount of power only is converted. Correct? The converted power is a P convert, and we know that omega m equal to PAG. Correct? PAG divided by omega sync. Correct? Omega S means synchronizing speed, rotating magnetic field, and this is the air gap. The power transferred from the stator to rotor to the air gap between the rotor and stator divided by this one is going to give, that can be written as 3 divided in 3-phase motor, you can divide by omega S into I2 square into R2 divided by S. This formula already we saw. It is nothing new you go to, right? So, however, if you remember the equivalent circuit, this is V5 input voltage. We are giving this stator. This is current I1, stator current. We are talking equivalent. This is JX1, stator reactance. R1 is the stator resistance. And JXM, magnetizing. And of course, you have another resistance, PRCL. Okay. This, okay. This is called as IM. And many times, if the this part is called as I2, which is going, this is the current in the stator, which is as a magnetic field transferred to the rotor. I2 is the current which creates the magnetic flux. That magnetic flux is transferred to the rotor, and so this is the rotor reactance. This is rotor resistance, rotor resistance referred with respect to stator. So it is always divided by S, where S is called a slip. This we know the equivalency already we saw that. Okay. Now this can be divided into this one. It can be reduced to we need to find out the induced torque. Induced torque, we always say I2, correct? If you see the equation, here our interest is to find out the I2. To find out the I2, we need to find out how much voltage is induced in the rotor, and then we have to find out what is equivalent circuit. So we need to find out the equivalent circuit of this. That's what we are going to see in the next slides. Okay, the equivalent circuit of this one can be found like this. So this is input voltage V5 given to stator. Because of there is I1 is flowing here, and this I called as R1. This is JX1 stator. This is JXM magnetizing impedance, and this voltage, the voltage across this part we call as V Thevenins. We say TH means Thevenin. Correct? Electrical students will know Thevenin. A scientist who found how to compute current, voltage flowing in electrical circuit. So V Thevenin's voltage. Okay, V Thevenin's can be computed into JXM. Note down this formula. In the exam, you can expect simple problem using this. V Thevenin is equal to JXM divided by R1 plus JX1 plus JXM. Okay, so please see that here we are neglected the this part. Correct. This effect is very little in case of this one. So copper loss in the rotor copper loss. Okay, so that is minimal. So compared to other things, so in the equivalent circuit, if you see that, this will be generally ignored. This will be generally ignored for the computational purpose. So only JXM will be shown, and this voltage is called as E1. They will call as E1. That is voltage in the rotor. This is input voltage. This is the voltage in the rotor. Sorry, XM is the stator. Where is E1 is this one? We know E2 is the rotor. This is E1. That is across this coil, this magnetizing coil. Correct? So we are measuring voltage across this, and that's what we are trying to find out. Okay. So Thevenin's equal can be written like this. So V Thevenin's, this can be further written V Thevenin equal to XM divided by root of R1 squared plus X1 plus XM whole square into V5. V Thevenin, because this is V5 is input voltage. If we know the input voltage we saw 440 volts or 400 volts in the previous problem. I think so. It is 400 volts we have referred. Correct? We know that XM was given, R1 was given, and X1 was given. Once it is given, you can always find out using the formula the voltage available at this point. Okay. So this can be, once you found V Thevenin, I can find the Z Thevenin. Next is find out the voltage. Then I also find out equivalent, this one, what you call the Z Thevenin of this circuit. Okay. That can be found Z Thevenin equal to JXM into R1 plus JX1 whole thing divided by R1 plus J into X1 plus XM. Note down this formula. Okay. So now that you found, so how will you find this one? In this circuit, to find out the Thevenin, correct? This Thevenin, what I do is, just carefully watch. this will be short circuited because voltage, what I'm seeing, I applied a VB. Sorry, they call V5. The input, correct? This is input voltage applied to stator coil, one coil. Because of that, there's a current is flowing, correct? Current is flowing like this. And there's a voltage up. We call VR1. This is VX1. And I can say VXM, correct? So because current flows, because there's a voltage drop across this, voltage across this, voltage across this. So my interest is I am measuring V Thevenin is nothing but voltage across this point only, correct? Across the XM only I am interested. So that can be found out using this formula. XM divided by the total impedance is nothing R1 square plus X1 plus is into V5 is the V Thevenin. So this voltage I found it. Now to find out the R Thevenin is nothing but we are looking from here. If you see what is the resistance of the entire this one impedance. In that case, what I do is to find out, I will do simply short circuit this. I think that there's no voltage source. Voltage source can be short circuited. If you short circuited, what you will see is no voltage source. R1 is there, JX1 is there, XM is there, and I'm seeing from here. In that case, we can see that this impedance or reactance is in parallel. These two are in series, correct? R1 and the series, so they are connected a series connection, and together this and this are in parallel, correct? This is that is R1 plus JX1 is in parallel with XM, correct? That is what the Z Thevenin. So in order to find out, we can use this formula. Okay. So how I found why this one methodology I am just showing. Okay. We don't nothing to get confused, but the thing is, I'm just showing what it is. That's nothing more than that. There's nothing to get confused, but I'm just giving you the. This is V5. I'm drawing the full circuit. This is the XM. This I call V Thevenin and also R Thevenin. Both are we are looking from this side in this. So, sorry, Z Thevenin. Because R means only resistance, here you have reactance also. So impedance we are finding Z Thevenin. So this can be found using this. Now, finally, what I can draw on equivalent circuit can be shown with V Thevenin we found out, which is connected to R Thevenin. This is coil. This is JX Thevenin. Because please note that Z consists of R plus JX. It is a complex quantity. Z will be divided in two parts. That's why we are showing you two parts. R Thevenin, nothing, don't get confused. Z Thevenin equal to R Thevenin plus JX Thevenin. So we can find out. Okay. So then that is connected to what? So this voltage is connected. This is going to be nothing but E2 and E1, and that is transferred to my rotor. That is R2 divided by S. This is going to JX2. Okay. So this is the final equivalent circuit to find the I2. Correct. So then we will be able to find out the induced torque using the formula. So we can write like this finally. This time now, just 2-3 minutes I will complete. So V Thevenin equal to, note down this formula in the exam. You can get simple problems. These are very simple problems. R1 plus J into X1 plus Xm. Similarly, Z Thevenin already we written. I'm just for comprehensive writing R Thevenin plus J X Thevenin, which is nothing but J Xm into already previous page written. I'm just writing all the formulas to find out the rotor current I2. For that, you need Z Thevenin, V Thevenin. Then only you can find out that R1 plus J X1 plus Xm. Okay. Shall I go or you are written down? Once this is known, V Thevenin, Z Thevenin, then I can find out I2. Shall I go to next page?
Yes, sir. We can go, sir. We don't note it down.
Okay. So I2 equal to V Thevenin divided by V Thevenin divided by R Thevenin plus R2 by S plus J into X Thevenin plus X2. Okay. For understanding, I will show you why. See, please note that all four elements, V Thevenin is the voltage going to be at the rotor. Thevenin, X2, R2, yes, all are in series. Okay. So that means the current is nothing but I2 is nothing but V Thevenin. This voltage, this current is nothing but I2. Okay. The current flowing from the V Thevenin. This is V Thevenin is a voltage source. A voltage induced in the rotor. Correct? It's called V Thevenin. Can be what already we know how to compute. Then from that, if you divide the impedance, net, this is called net impedance of the stator plus rotor. Because the current voltage actually into given as the V5 as given only in the stator. From there only everything is happening. Finally, I2 also we are getting like this. So that means I2 can be computed using this formula. So I2 can be written V Thevenin divided by root of R Thevenin plus R2 divided by S. Please note that Z equal to R plus X. Okay. Here, R you have two components, resistive part. R Thevenin, that means these two can be added. Correct? These two can be added. Similarly, these two are, that's what is shown here. So, and to find a equivalent, the Z, you know that Z equal to root of R square plus JX square. Already you know, that's what we are trying to do. Plus the X will be removed, correct? To remove that, X Thevenin plus X2 whole square. Complex quantity we are trying to make as a real part. R Thevenin, this one. Okay. So now that we know I Thevenin, so we can say that tau induced equal to PAG divided by omega S equal to 3 into V Thevenin square divided by omega S into R2 divided by S whole thing divided by R Thevenin plus R2 divided by S whole square plus X Thevenin plus X2 whole square, the bracket, to find out the T induced. If you know PAG is known, then you can find out using this, because the whole thing talks about PAG. Okay. Let me stop here. In the next class, we will discuss little more about the controlling the motor and how the external resistor adding in the rotor, in wound rotor, will improve the torque. starting talk, all those things we'll see in the next class. I will stop here. Have a nice weekend. We'll see you on Monday. Okay. Please give your attendance before leaving without fail.
Okay, sir. Okay, sir.
Okay.
Thank
Take
you, sir.
care. Thank you.
Thank
Thank you, sir.